Hello everyone, I'm Bing Tian from Alibaba, and I just received my PhD degree in Nanjing University. Today I'm going to present Aquila, a practically usable verification system for production-scale programmable data planes. This is a joint work during my internship at Alibaba with my colleagues from Harvard University. As a prominent online service provider, Alibaba operates a global network infrastructure serving over 1 billion customers. As services today constantly evolving in size, it's becoming increasingly difficult for edge networks to handle the ever-growing traffic due to resource constraints. This promoted us to offload a group of network functions from servers to save CPU resources and get better performance. Recent advances in programmable networks have enabled us to implement network functions using P4 language. It gives us a cost-effective solution to greatly improve the performance of our edge networks in terms of both functionality and efficiency, as well as flexibility. Given these advantages, we have widely deployed programmable switches in our edge networks. With the increasing diversity of our services, the data plan programs are greatly increasing in complexity. Each program may consist of thousands of lines of P4 code and multiple pipelines, and each pipeline holds a number of network functions, such as NET, load balancer, and DDoS defense. The network functions across different pipelines are tangled with many packet paths, resulting in complex function chains within the single switch. Therefore, it's a great challenge for developers to ensure the correctness of data plan programs. To prevent any possible data plan bugs, we need a practically usable verification system to rigorously verify the correctness of data plan programs. To make the verification system practically usable, a simple and powerful language is required to help developers write their intent in an easy way. The verifier should be able to verify production-scale data plan programs and give results within a tolerable time. When the verification task fails, the verifier should try to localize the bug, instead of just printing a counterexample on the trace. And last, the verifier should be confident to its verification result, and try to avoid false positives and false negatives. The above 4 points correspond to our 4 challenges. The first challenge is about the intent complexity. It's not easy to describe some intent accurately in a simple way. For example, see this intent. For each TCP packet, we shouldn't change its TCP header. It's very natural for us to understand it. But from a verifier's perspective, what's the definition of the TCP packet? Is a packet with TCP header a TCP packet? Or a specific header order is required? Here, of course, the second packet is not what we want, but it's not easy to tell this point to the verifier. If we follow existing work, we will have to write a lot of lines to express this intent. It's very complex and also error-prone. It would be much better if we can express it in one line. The second challenge is about the scalability. Our production programs are composed of a layer 3 switch and a lot of network functions. It's not easy to verify such a big program efficiently. In addition, our production programs are mainly written by P416. Unlike P414, P416's match action units are divided into 2 logical pipelines. Each pipeline has its own parser and deparser. Unfortunately, it's exactly the parser and deparser that contributes the major complexity to verification. Existing works are not scalable to our production P416 programs. The next challenge is about bug localization. When the verification task fails, existing work only print a counterexample and a bug trace. However, it's not enough. In our production programs, the bug trace contains over 100 steps, and it's still very hard for developers to localize the bug. The last challenge is about the reliability of the verifier itself. A verifier can also have bugs, which may mask the program's bug. So a validation mechanism is required to make the verifier more reliable. But no existing P4 verification system can do self-validation. To solve all above challenges, we built a production-scale data plan verification system, Aquila. Based on our experience in developing P4 program, we designed a simple and powerful intent language to help developers describe the desired property. Next, we proposed a set of encoding algorithms to translate P4 programs into a guarded command language and solved the scalability problem. Then, we reused the verifier to build a bug localization algorithm by analyzing the causality of the bug. And last, we use a cross-checking algorithm to validate the correctness of the verifier. Now, I will introduce the first part, the intent language. The key insights of intent language are summarized from our experience. For example, we noticed that the most intent can be placed before a pipeline or after a pipeline, but seldom inside the pipeline. This gives us a chance to represent the intent as a single independent file, instead of adding annotations in P4 code. With our intent language, developers can easily describe the properties about parsers, match action units, and program architecture. Next, I will introduce how to make the data plan verifier fast and scalable. We use Dijkstra's classic method to verify a program, so we make no claim on the novelty of verification technology. Instead, our contribution is how to encode a P4 program to another program that can be efficiently verified. To achieve this, we need to solve a lot of problems. In this talk, I will only introduce the state explosion problem of the packet parsers. Look here, here is a packet parser, and it's also a state machine. In each state, the parser extracts corresponding packet header and then transits to another state according to the field of the header it parsed. Look at this transition. It's not a typical branch structure because it has two parallel exits. That means we can't express it with the if statements. A straightforward way is to expand the state machine into the tree, so that we can easily express the tree with the if statements, and then it's trivial to verify the program. However, we can see that at the bottom of the tree, two states are duplicated. It's okay for small programs, but not acceptable for large programs, because the tree can be very deep. In the worst case, there can be over 1,000 duplicates. Verifying such a malformed program requires a lot of memory and several days. To solve this problem, we proposed sequential encoding to reshape the state machine. Let's assume the parser is acyclic, so that each state can be visited at most once. In addition, for any two states, they are either mutually exclusive or have a fixed order of execution. That means the acyclic parser can be regarded as a sequence of states. Each state can be visited once or not visited, depending on previous states in the sequence. For example, whether to visit the TCP state depends on the protocol number from IPv4 or IPv6 state. Whether to visit the IPv4 state further depends on the Ethernet type from Ethernet state. Here is an example of sequential encoding. We use the following 4 steps to translate a state machine into a simple verifiable program without any code duplication. There are some details remained. For example, how to encode external functions, and how to handle the parser loops. In this talk, I will skip these details. You may find them in our paper. Now, let's see how Aquila performs. We choose invalid header access as benchmark to evaluate Aquila's verifier, and record the time to find the first bug and find all bugs. From the results, we can see that without Aquila's encoding algorithm, it's almost impossible to verify multi-pipeline programs with complex parsers. Finally, I will use a real example to show how Aquila is used in Alibaba's pivot verification. Here are the pipelines of production-scale data plan programs. Layer 3 functions are implemented in switch ingress and switch egress, while custom functions such as load balancer are implemented in LB ingress and LB egress. One day, our developers need to decapsulate VXLAN packets in LB egress and then route the decapsulated packets. But routing tables are placed in switch ingress. There is no hardware resource to place another routing table in LB ingress. To solve this problem, our developers decided to swap the switch ingress with LB ingress. This changes the dependency between the two pipelines. For example, the net function is originally placed in LB ingress, while the echo function is placed in switch ingress. After the swapping, the echo table will match the netted address instead of the original address. We use Aquila to verify whether the semantics of each function are equivalent before and after the swapping, which proves that Aquila is practically usable in verifying production-scale data plan programs. In conclusion, Aquila is the first practically usable verification system for production-scale programmable data plans. It provides a high-level specification language, a fast and scalable verifier, a bug localizer, and self-correctness guarantee. Aquila has been used in Alibaba for more than 1 year, and found several bugs in our data plan programs. This is the end of my talk. Thanks for listening.